Hi everybody, welcome to Enigma. I'm certainly glad to be here. So I'm going to be talking today about the limits of sandboxing and the next steps after that. I'm Chris Palmer from the Google Chrome security team. I want to note that the slides have a lot of links and the speaker notes have a lot of links. And so you can get the Google Doc originals by clicking on this from the PDF that Enigma will publish. So I'll start by giving a bit of information about me, where I come from. My name is Chris. I work on Chrome security. I've worked here for almost a decade, and in that time, I've done a variety of stuff like web PKI and secure usability, HTTPS deployment, web platform security, and more. These days, I work on the Chrome platform security team. My goal for this presentation is to describe our experience pushing sandboxing, pushing the boundaries, and the lessons we've learned doing so, and what we think the future holds based on that. I hope this provides guidance for software architects, engineers, and the people who fund them. My team's work is to defend the people who use Chrome against what I call attacks against the mechanisms, as opposed to attacks against people and their relationships. By attacks against people, I mean things like phishing, OAuth phishing, malicious downloads, and other social engineering attacks. These are very powerful and effective attacks, obviously, and Chrome has several teams dedicated to defending against them, and I think they've made great advances in the state of the art. But by attacks against mechanisms, I mean things like exploiting memory unsafety, escaping the sandbox, finding techniques for persisting across reboots, low-level security logic bugs, and so on. Alex Gaynor talked about the nature and prevalence of memory unsafety. For this presentation, our problem is that C++ is a slippery and unsafe language, and the purpose of web browsers is to run web content and code as fast and as efficiently as possible, which makes the risks of unsafe languages particularly acute, I think. Malicious websites and networks can get a surprising amount of control over the processes that interpret them. And as Alex mentioned, attacks against the mechanisms are not uncommon. So first I'll talk a bit about what sandboxing is. So here's a picture from Chromium's public documentation. It shows that sandboxing, or privilege separation and reduction, is when you break an application into two or more parts, one or more lower privileged processes and one or more higher privileged broker processes that mediate access to the system on behalf of and in defense against the lower privileged processes. The goal is to contain the damage when malicious web content compromises a process. Interprocess communication, or IPC, is critical to this design. IPC introduces significant complexity and an efficiency cost, but they're worth it. Sandboxing is absolutely necessary for a variety of software, including browsers, operating systems, virtual machines, application servers, and so on. Chromium's usage of the term is distinct from its usage in the contexts of, say, Android or iOS. We mean not just reducing the privileges of an application, but more, breaking an application into multiple parts and minimizing the privileges of each part. In Chromium, the biggest difference is between the browser process that has full privilege and the many lower privileged renderer processes. They interpret and render website contents, and we give them as little privilege as possible. In Chromium, we separate each website into its own distinct sandbox, separate from the browser, network, and GPU processes, and separate from other websites. Sandboxing contains the damage of memory unsafety and other bugs. It also reduces the available attack surface of other processes, and the kernel. These two benefits are complementary. It is also a good defense against logic bugs, though. For example, if there were a gap in the same origin policy enforcement logic in the renderer, sandboxing would contain the damage because the attacker would still not be able to automatically, without any other bug, get into cross-site origins hosted in other processes. A same origin policy bypass or memory unsafety exploit in the browser or network service process, which I'll talk more about in a moment, can still be effective cross-origin, though. This is a known gap due to practical limitations, and more on that later. Okay, So having said all that, good sandboxing is table stakes. It's extremely necessary to contain those classes of bugs I was just talking about. Although this talk is about the limits of sandboxing, I would like you to bear in mind several important things. One is that what limits a web browser running on mainstream operating systems might not be a limit for you, might not limit your application. You might be on a platform that's more amenable to fine-grained sandboxing, like maybe Linux. I'll talk more about that later. And although we're pretty sure Chromium is close to the practical limits of mainstream operating systems on mainstream hardware, your application might still have significant sandboxing headroom, so to speak. And I'd urge you to make sure you're using all of that first before going into other more difficult stuff. So how do you build a sandbox at all? The fundamental building block available to us is the process boundary. We have to use whatever primitive mechanisms the platform provides. Essentially, a sandbox process unilaterally reduces its own privilege before it begins processing untrustworthy data and code. It maintains a channel to the broker process to request services, much as a user space program requests services from the kernel via system calls, for example. To build a sandbox, we use whatever is available to us on each platform. What mechanisms are available vary widely across platforms. Windows is very different than Linux, and although Android is based on Linux, it's still a very different thing. And there's different APIs available and so on. So another nice thing would be if we could get securely segmented memory inside a single process, and that might enable us to make finer grained sandboxes for cheaper. I'll talk a bit more of that in a moment. So on Android, what mechanisms are available to us? A key thing is the isolated process mechanism, which we asked them for, and they kindly provided it. And it's a public API, of course, you can use it too. And they also provide via seccomp BPF some predefined limits to system calls. We can apply those to renderers, and then they can do less with the kernel. And again, you can use those too. On Linux and Chrome OS, it's a different story. We use seccomp BPF again to filter system calls, but we can do so at a finer grain. We can make arbitrary policies that suit our needs. And we also make use of user namespaces, which is a very nice feature that we've gotten a lot of benefit from, but it comes with its own costs. There may be still some bugs in the kernel that are available to processes that are using user namespaces, for example. It's not perfect, but it's what we got. And again, all of our code to do this is open source, and it's more or less an independent, separable module in the Chromium source code tree. Firefox uses parts of it, for example, as does Adobe Reader. And if you need help, you can mail us at security-dev@chromium.org, and we'd love to help you out. So there are limitations and costs to doing all this, though. Unfortunately, we can't just put a sandbox on everything. So like I said, processes are the minimum unit of isolation on a mainstream OS. And unfortunately, while processes are really cheap on Linux and Chrome OS and Mac OS, they're kind of expensive on the platforms that are most populous, Android and Windows. A process can be quite large on Windows and very large on Android, and the process startup latency can actually be so big that it makes user experience visibly janky. We don't want that. It's a big problem. But on Linux, processes are nice and cheap, and that can be very beneficial to you if you're sandboxing a server application that you're running on Linux, for example. You could do finer grained sandboxing. I'll talk a bit more about that. So how do you decide when to sandbox something, when to isolate it? We have a plan, and that plan is called site isolation. We don't just create new renderers ad hoc. For your applications, you'll want to define some reasonable granularity of isolation, whether it's per user account, per customer, per request, or in a time period, or something else like that. So here's a picture of how we break things down. This sequence of slides comes from my colleague Adrian Taylor, so we can thank him for that. First, there's the browser process. It has full privilege. Then if you load 3 websites, you get 3 renderers, each hosting that site. The idea is that a security breach from one site can only affect the one renderer process. But we learned that we also need a GPU process to talk to the operating system's GPU driver and so on, and that needs to be separate from the browser. It has different privileges. And we also decided to put network handling, like TLS client, quick client, and things like that, DNS handling, in its own process, the network service process. Previously, that was in the browser too, and that obviously handles a lot of untrustworthy data from the network. So we're separating that out. But note that this one network process still handles all networking for all web origins and all websites. So you could imagine going further, right? You could imagine giving each renderer its own network process. We haven't done this yet. We don't think it's affordable right now, but it might be cool someday in the future. Similarly, we have a separate storage service process for things to support things like cookies, local storage, IndexedDB, and things like that. And again, that process handles storage for all sites. So all the renderers send IPC messages to it to get access to their stored stuff, and we need for there to not be bugs there. Someday you could imagine that we give each site its own storage process. That would be cool. We can't do that right now. So the same process of breaking things down, everything being backed by every site being backed by its own stuff. You can imagine that going further with that, all the privileged backends that support web platform features like WebAuthn, web payments, web USB, things like that, might get their own distinct processes per site someday. But pretty soon you could be talking about, maybe dozens of processes for each site that you load. And that could get too expensive, certainly is right now. On some platforms where processes are cheap and hardware is plentiful, a design this fine-grained might be possible, possibly for you. But for Chromium right now, it's not. You should be thinking along these lines, though, for your application. So how do you move forward given these limitations? We think the future is all about memory safety. As necessary and as good as sandboxing is, it can never be sufficient by itself, and it's not arbitrarily applicable, as we've seen. For example, there's still significant browser and kernel attack surface that's available to a compromised renderer. Similarly, the network service process must still process untrustworthy inputs from the network and from all web origins. And it has a lot of user state in there. So therefore, we need to not just contain bugs, but to mitigate and hopefully even solve them. So to do that, we're investigating safer language options. Obviously on Android, we already use Java, and we might use Kotlin someday. On iOS, we make a use of a little bit of Swift. You can imagine growing that. Rust would be very cool. We are thinking about WebAssembly to get a form of segmented memory, kind of, it can contain the damage of memory corruption, for example. So you could imagine doing more with Java and Swift, for example, but that would entail duplicating implementations, one for Java on Android, one in Swift for iOS, and then again C++ for the other platforms, because we don't plan to use Java on Windows, for example. Alternately, you can sanitize or normalize an untrustworthy input in Java or Swift or a safe language before passing the input to C++ for further processing, and only if it passes the sanitization layer, for example. And we sometimes do this on Java, on Android and Java now. But note also that sometimes the Java or Swift APIs that the platform gives you might just be thin layers on a large body of C++ code underneath. And without a sanitization phase, we wouldn't consider that to be safe. That doesn't count as a safer language. Also in 2021, we're going to be experimenting with WebAssembly, and it might give us developer ergonomics and efficiency and safety enough to just put our existing C++ code in a little box. That would be very fruitful if it works out. Firefox is pursuing a similar strategy, for example. So then the question arises, how do you migrate to memory-safe languages? It's not all or nothing, thankfully. That'd be a huge undertaking. As Alex explained, you don't need to migrate everything all at once or even ever. A big problem for Chromium is interoperability. We want to be able to integrate Rust with C++ or Swift with C++ easily. It has to be efficient and ergonomic. There is some progress in that area. The CXX module from David Tolnay, for example, makes Rust and C++ interoperability a lot easier than it has been in the past. There's also the question of the learning curve. A language that can solve the problems that C++ can is likely to be roughly as complex as C++, even if there are fewer pitfalls. Chromium engineers have spent a long time learning the Chromium dialect of C++, and learning an additional language to the degree of competence necessary is, it's hard, it takes time. But I definitely think it's worth it, and we should be doing it. In any case, if you're starting a new project, you can start right now with a safer language. And similarly, projects that are smaller than Chromium have a comparatively easier job. It's not going to necessarily take you a huge amount of time, like not necessarily a decade. And then again, interoperability with vanilla C is typically easier than with C++. So another thing we're looking at doing is improving memory on safe languages, C++. We have smarter pointer types that we're working on. One is called Miracle Pointer, and we are working on garbage collection, expanding the use of it. We have a garbage collector called OilPan. We're going to be using it in PDFium soon. And a semi-GC-like technique called Miracle Scan. So, we want to be able to ship improvements this quarter, right? Not just in 10 years. So we need to work with the C++ that we've got. First, we know that use after free bugs, especially in the browser process, are a key problem for us. For that, we have two leading options, Miracle Pointer. It should make UAF, use after free, not deterministically exploitable. Miracle Scan or Star Scan is like GC in that it looks for additional references to an object on the heap, and then if it finds any, it puts the object in a quarantine rather than destroying it so that it can't be used after free. Prior work along those lines includes MarkUs from Cambridge and MemGC from Microsoft. The time and space efficiency of these approaches seems to be within range of shippable, and we're testing that now. But additionally, hardware vendors are helping out. We intend to make as much use of memory tagging and control flow integrity features as is possible when they become widely available, which might be soonish. Emulating these features in software is helpful, but it's never going to be as efficient as with hardware support. So when that comes, we'll be very happy. So what are the implications of all this? We have to get to the acceptance stage of grief, as Alex described. We have to accept that the technical debt of unsafe languages has come due. So here's a picture of what that looks like for us. This is a picture of high and critical bugs in Chromium. You can see about a third of our bugs are use after free. Another third is other memory unsafety. Roughly a quarter is other bugs. And security-related asserts, like in V8, checking logic to be sound, is about 7%. So overall, platform security teams throughout the industry, Microsoft, Mozilla, Android, Apple, they're seeing the same problems and at roughly the same scale. 2/3 to 3/4 of security-relevant bugs are due to memory unsafety. And in general, everyone seems to be looking in the same direction, to further reduce privilege with sandboxing and increase memory safety. These techniques can create significant asymmetries that favor the defense, I think. Attackers would be less and less able to get what they want with a single bug. They'd need a chain of bugs to get a successful exploit, longer than now, harder to find than now, hopefully. And each bug would be harder to find and reliably exploit. Thanks again to Adrian Taylor for this picture, by the way. So the future for us, we think sandboxing has given us a great first 10 or more years. The next 10 require more, and we think that's memory safety. Beyond that, though, my own dream is for attackers to have to fall back to exploiting bugs that are actually in the application domain of a browser. Bypassing same origin policy enforcement logic, for example, is an example of that, as is spoofing authentication, confused deputy attacks using IPC, like tricking the browser into thinking that one site is another site, things like that. Then we can build on memory safety and try to resolve those higher level bugs with higher level defense concepts such as type safety, formal verification of protocols, and advances in secure UX design, things like that. All these things are progressing in parallel. We're doing all of these things. But our hottest fire right now is memory unsafety, and so that's where we're headed, we think, for the next decade. So thanks for listening, and I'll take questions now.